Hai semua, selamat datang ke sesi penerangan kita kali ini. Hari ini kita nak rungkai satu rahsia kejuruteraan yang tersembunyi, tapi sebenarnya ia membentuk hampir ke semua barangan plastik yang ada di sekeliling kita sekarang. Jom kita mula. Cuba bayangkan, lebih daripada 70% daripada jumlah tan plastik komersial kat dunia ni sebenarnya melalui proses penyempritan berterusan atau continuous extrusion yang kita nak bincangkan sekejap lagi. Bayangkan betapa besarnya jumlah tu. Ia betul-betul tulang belakang kepada industri pembuatan moden kita.
Okey, ini peta perjalanan kita hari ini. Pertama, revolusi pembentukan plastik. Kedua, anatomi mesin penyemprit. Ketiga, zon suapan. Keempat, zon mampatan. Kelima, zon pemiteran. Dan akhir sekali, matematik di sebalik penyempritan.
Kita masuk bahagian pertama, revolusi pembentukan plastik, menggantikan logam dan kaca.
Pernah tak anda terfikir kenapa plastik banyak gantikan bahan pembungkusan tradisional macam botol kaca dan logam? Jawapan pendeknya, kecekapan. Proses plastik ini guna suhu yang jauh lebih rendah, maksudnya kita jimat tenaga yang sangat banyak berbanding logam. Tambah pula cara nak kendalikannya masa pengeluaran memang jauh lebih mudah. Dan yang paling ketara, selalunya ia tak perlukan langsung proses mengecat selepas ia dikeluarkan. Sangat praktikal kan? Okey, bahagian kedua. Anatomi mesin penyemprit, memecahkan mesin. Prosesnya bermula macam ni. Bahan mentah akan jatuh dari corong di bahagian atas tu, terus ke atas skru di dalamnya. Skru yang berputar laju ni bertindak macam jantung mesin penyemprit. Ia sentiasa tolak plastik yang perlahan-lahan mencair tu ke depan, melepasi beberapa zon pemanasan, sampailah ia keluar melalui acuan di penghujung mesin yang beri bentuk akhir pada plastik tu. Tapi tunggu sekejap. Sebelum kita ikut perjalanan pelet plastik ni dengan lebih rapat, kita kena faham dua perkara asas pasal bentuk skru ni. Pertama ialah diameter akar. Ini cuma diameter batang tengah skru tu. Kedua ialah kedalaman bilah, iaitu jarak menegak dari bahagian paling atas bilah skru ke diameter akar tadi. Ingat dua terma ni ya, sebab ia akan bantu anda faham keseluruhan proses ni. Nah, ini yang paling menarik. Perhatikan betul-betul macam mana ruang dalam skru tu berubah. Saiz tongkat luaran tu memang tetap, tapi bila diameter akar di dalam tu makin membesar, kedalaman bilah secara automatik makin mengecil. Hubungan bentuk geometri inilah rahsia yang mewujudkan mekanik luar biasa di sepanjang tong penyempritan ni. Kita masuk bahagian ketiga, zon suapan pengambilan, memulakan perjalanan. Kalau anda nak tahu, rekaan mesin penyemprit yang paling popular dalam industri sentiasa dibahagiankan kepada 3 zon utama. Setiap zon ni ada tugas mekanikal yang sangat kritikal. Langkah 1 adalah penyuapan, langkah 2 adalah mempatan dan langkah 3 pula adalah pemiteran. Kita mulakan dengan zon suapan. Dekat sini, saiz diameter akar memang sengaja dibuat kecil. Kenapa? Sebab kita nak cipta kedalaman bilah yang besar dan kekal saiznya. Ruang yang luas ni penting gila untuk tarik bahan resin pepejal yang masih berketul-ketul tu turun dari corong dengan lancar dan mula panaskannya. Boleh bayangkan zon ni macam ruang penerimaan tetamu lah. Seterusnya, bahagian keempat. Zon mampatan, picitan, memplastikkan bahan. Okey, fokus kat poin ni sebab ia sangat penting. Masuk je zon ni, diameter akar tadi tu secara perlahan-lahan mula membesar. Jadi ruang dalam tu makin sempit dan kedalaman bilah pun jadi makin kecil. Proses ni akan perah resin tadi secara fizikal dengan sangat kuat sampai ia jadi plastik cair sambil paksa apa-apa udara yang terperangkap dalam campuran mentah tu untuk mengalir ke belakang. Tindakan perah ni bukan sekadar nak cairkan bahan tau. Ia sangat-sangat penting untuk integriti struktur plastik tu nanti. Bayangkan kalau kita gagal buang gas atau udara yang terperangkap ni, produk akhir yang sampai kat pengguna nanti akan ada kecacatan macam berongga, berliang dan tak kuat langsung. Bergerak ke bahagian kelima. Zon pemiteran, tolakan terakhir, menghomogenkan leburan. Sampai je di peringkat akhir ni, plastik kita yang dah cair tadi ditolak kuat masuk ke dalam zon pemiteran. Skru di sini ada kedalaman bilah yang sangat cetek dan saiznya tetap. Ruang yang sempit ni tak dibina saja-saja. Ia sebenarnya wujudkan daya ricih atau shear yang sangat tinggi untuk betul-betul cairkan baki pepejal yang ada, campurkannya sekata dan tekan resin tu sekuat hati untuk bersedia keluar. Dan di sinilah keseluruhan proses mekanikal tadi mencapai kemuncaknya. Macam yang anda boleh agak bila ruang fizikal skru tu jadi semakin cetek dari zon suapan sampailah ke acuan, tekanan di dalam tong tu secara drastiknya akan naik mendadak. Tekanan melampau inilah yang tolak produk akhir tu keluar tanpa henti.
Tapi ingat, geometri skru yang hebat ni mesti diubah suai ikut jenis bahan tau. Contohnya, polietilena cair secara perlahan-lahan, jadi ia perlukan skru di mana panjang setiap zon dibahagi sama rata. Sebaliknya, nylon pula cair dengan sangat mendadak. Jadi untuk nylon, kita perlukan skru yang profilnya diubah suai dengan zon mampatan yang sangat pendek.
Dan yang terakhir, bahagian ke-6, matematik di sebalik penyempuritan, tarik tali mekanikal.
Jom kita lupakan sekejap zon fizikal tadi dan tengok sikit pengiraan matematik yang menggerakkan keseluruhan proses ni. Cuba bayangkan keadaan dalam mesin ni macam satu perlawanan tarik tali yang sangat sengit. Dekat satu pihak, kita ada aliran serit atau QD. Ini adalah daya pam berterusan yang gerakkan polimer ke depan. Tapi kat pihak lawan pula, kita ada aliran tekanan atau QP, iaitu rintangan dari acuan tu yang menolak kuat ke belakang menentang aliran tadi.
Jadi, pertembungan dua daya inilah yang menentukan segala-galanya. Output mesin kita atau kadar aliran isi padu bersih sebenarnya hanyalah hasil gabungan matematik ringkas bagi dua daya yang bertentangan ni. Sebab itulah, nak kawal kelajuan putaran skru adalah sangat kritikal.
Memandangkan proses penyempuritan berterusan ni tak putus-putus hasilkan barang yang kita guna tiap-tiap hari, ia tinggalkan kita dengan satu soalan yang cukup menarik. Dengan dunia yang mula beralih ke arah kelestarian, agak-agak macam mana teknologi mekanikal hebat skru 3 zon ni akan berevolusi dan diinovasikan untuk kendalikan bahan komposit baharu yang lebih mesra alam pada masa depan. Sesuatu yang sangat menarik untuk kita renungkan. Terima kasih sebab sudi luangkan masa bersama saya dalam sesi penerangan tentang mesin skru penyempuritan ini. Jumpa lagi.
Welcome to This Explainer. Okay, today we're taking a seriously fascinating journey. We're going to see how seemingly dry academic physics translates directly into the massive, heavy-duty machinery that shapes, well, practically everything in our everyday plastic world. We'll be tracking the incredible transformation of a simple, hard little plastic pellet into an endlessly flowing river of material, all to uncover the absolutely brilliant engineering making it happen. Okay, let's dive into this. Here's our roadmap for our material science journey today. We'll start with shaping our plastic world, then we'll meet the polymer melt, explore the continuous extrusion process, step inside the extruder machine itself, and finally, we'll talk about erasing the plastic memory.
So, let's kick things off with Section 1, Shaping Our Plastic World.
You know, over the last 50 years or so, the applications for plastics have just exploded, growing way faster than traditional materials. In fact, the sheer volume of plastics and rubbers produced globally actually outpaces metals and ceramics now. Crazy, right? And the big reason why comes down to one word: efficiency. Plastic molding is what engineers call a net shape process. And let me tell you, this is a massive game changer. It literally means that parts come out of the machine perfectly formed right from the get-go. No extra shaping, cutting, or drilling needed. Plus, because we're working at much lower temperatures compared to melting down heavy metals, it uses significantly less energy. Oh, and you usually don't even need to paint or plate the final thing. It's basically manufacturing at its absolute most efficient.
Now, to really understand this, we need to meet the protagonist of our story, which means looking at the two main types of plastics. On one hand, you've got thermosets. These undergo permanent chemical cross-linking when heated. Basically, once they cure, their structure is permanently locked in, kind of like baking a cake. You can't unbake it. But thermoplastics? Oh, they're a whole different story. Their chemical structure doesn't change when they get hot. They can be heated, softened, and reshaped over and over and over again. Because they make up over 70% of the total commercial plastic tonnage out there, thermoplastics are, without a doubt, the undeniable star of this explainer.
Moving right along to Section 2, Meet the Polymer Melt. Now, what's really interesting about this slide is how we chart the actual fluid dynamics of our melted plastic. If you look at that top curve, you'll see it doesn't behave like water. Water is a Newtonian fluid. It flows consistently. But a polymer melt, it's what we call a pseudoplastic fluid. Its viscosity actually drops at higher shear rates. To put that in everyday terms, the harder and faster you push it, the thinner it gets, and the easier it flows. It's completely counterintuitive, but so cool.
And that brings us to the second crucial rule of our melts world, which is mapped out for us here, plotting viscosity against temperature for various polymers. You know, things like acrylic, nylon, polypropylene. The big takeaway is super simple but incredibly vital. Just heat it up and it flows easier. Combine these two rules, push it hard to create shear, and heat it up, and they literally dictate exactly how we have to build our massive manufacturing machines to handle this thick, high molecular weight fluid.
Which leads us perfectly into Section 3, the continuous extrusion process. So, taking those physics and putting them into practice, this extrusion process is just a relentless, continuous shaping operation. It works by taking that molten plastic and forcing it under immense pressure through a specifically shaped opening, which we call a die. This is exactly how the world mass produces things you see every day, like continuous tubing, PVC water pipes, giant flat sheets, and even the rubbery coating wrapped around electrical wires. Now, a rotating single-screw setup housed inside a giant electrically heated barrel is your standard workhorse here. Although they will swap in a twin-screw system if they really need superior mixing for, say, special resins or fillers.
Let's get a closer look in Section 4, inside the extruder machine.
Let's move to and see how this builds pressure across the 3 distinct zones of that rotating screw. Step 1 is the feed section. This is where dry, bulky feedstock pellets drop in from a hopper and get moved along and preheated. Step 2 is the compression section. This is where the magic happens. The polymer physically transforms into a fluid. Anti-trapped air mixed in with the solid pellets gets squeezed right out, and the whole mess is heavily compressed. And finally, Step 3, the metering section. By this point, the melt is completely homogenized and huge amounts of pressure are developed to pump it out through the die. To pull this off, the depth of the screw channel actually steadily decreases from the feed end all the way down to the die end, just relentlessly building up that pressure.
To really grasp the sheer scale of this journey, let's look at a little bit of the math behind the machine. Don't worry, it's not too complicated. We're looking at the LD ratio. That stands for the length of the flighted portion of the screw divided by the inside diameter of the barrel. This typically sits somewhere between 16:1 and 32:1. Now, this ratio is incredibly important because it essentially measures the machine's pure capability to mix materials and successfully melt down hard-to-process, bulky solid resins over a long physical distance.
Next up, we have the compression ratio. This compares the deep flight depth back in the feed section to the very shallow flight depth up in the metering section. This is typically around 2.25 to 1. So the crucial point is that this ratio measures the actual mechanical work and high shear that's forced onto the resin. As that flight depth dramatically gets shallower, the intense shear friction builds pressure and physically heats the resin from the inside out. It makes it flow exactly like those pseudoplastic physics graphs we looked at earlier. Predicted. It's brilliant.
And that brings us to the climax of the process. Section 5, erasing the plastic memory.
Right at this exit point, right before the plastic shoots out, let me pose a real-world problem to you. Why do some extruded plastic parts, like say thick parquet flooring blocks, occasionally come out of the cooling bath completely twisted and warped? I mean, it's a bizarre defect that completely ruins the product, but it reveals a hidden, really stubborn secret about the nature of the plastic molecules themselves.
The solution to preventing that warped, twisted plastic actually lies in a specific component placed right before the die, the breaker plate screen pack. Now sure, it does basic maintenance stuff, it sieves out unwanted dirt to protect the incredibly expensive die, and it helps develop head pressure. But look closely at point number 3. It removes the turning memory from the melt. You see, polymers are basically made of long, coiled chain molecules. As they travel down that turning, spiraling screw, they naturally align and actually retain an elastic memory of that twisting motion. So if you don't use a perforated breaker plate to essentially wipe its memory clean and physically break up that coiled plug of polymer, your final product will literally try to twist itself back into a spiral.
And this brilliantly illustrates a related, just fascinating concept, die swell. Because even after passing through the breaker plate, the plastic never truly forgets its elastic nature. Thanks to viscoelasticity, which is this unique combination of thick liquid viscosity and bouncy elasticity, the hot plastic physically expands, or swells, the exact second it's freed from the restricting pressure of the die opening. It just pushes out and puffs right up.
As our source material beautifully and simply states, polymers are made up of long-chain molecules, coiled. They have a tendency towards elastic recovery. This underlying viscoelastic tension means the plastic is literally always fighting, even just a little bit, to go back to its preferred relaxed shape. So, I'm going to leave you with this provocative thought as we wrap up today. How many perfectly straight, rigid, everyday extruded plastic objects sitting around you right now are secretly hiding this invisible elastic tension, just waiting for a chance to spring back? Thanks so much for joining me on this explainer. I really hope you never look at a simple piece of plastic the exact same way again.